Okay, Professor Jamison-Hooks here, and we're back with our single digital down converter, and we're going to take a deep dive into it and sort of look at different components of it a little deeper so that we could increase our understanding of digital signal processing. I teach a course called Signal Processing on FPGAs. So this by no means is a comprehensive digital signal processing course, but I'm showing how signal processing shows up in on FPGAs and things that we need to be mindful of. All right, so if you haven't watched my previous videos, please do. We are exploring 3I Atlas. We're having fun with this interstellar object. We're imagining that it holds a magical frequency that we're calling F1. And we're saying that F1 may be the healing power that we need in our life right now, or that peaceful harmonic that brings peace on earth. And we definitely need that right now. So we're looking at how does our signal get affected, because a digital down converter is something that is widely used in radar, astrophysics, astronomy. So sometimes we want to see a specific feature that is in an orchestra of frequencies. So we use a digital down converter for this particular application. So our incoming signal from 3I Atlas is in the time domain. We go into our ADC, which takes it into the discrete domain, which we can now implement our mixer, our filter, and our downsampling items 1, 2, 3 on a FPGA. And so what we're looking at is, first of all, this mixer, which we will then start to see that a mixer is actually a frequency translator, is also known in the industry as an LO, a local oscillator. All right. So the first thing we're going to do is kind of look and see how many FPGA resources does a single down converter consume. All right, so we're looking at the Xilinx RF SOC FPGA, and we're imagining we have a bandwidth of 500 megahertz, a sampling rate of 1.1 gigahertz. And so these are the major resources that we are consuming. These lookup tables, we're using about 7K to 12K lookup tables, 7,000 to 12,000. DSP slices are dedicated multiplications and addition blocks that don't eat up our precious lookup table blocks. And they're dedicated on FPGAs so that we can do our complex mathematics, which is what DSP is about. And so we're using 28 to 36 slices. All right. And our block RAMs that we're using is 2 to 4. So right here, I want you to take a moment and go and look up the Xilinx RF SOC FPGA and find out the maximum amount of resources that we have available to us so that we can then start to see how much are we eating up, okay? So now, let's see. So what's happening? Okay, so now we're going to go to a deep dive, but I've already done this, but now I'm putting mathematics to this a little bit because the language of DSP is mathematically rich. And without it, when we try to bypass the mathematics, well, you're bypassing the entire discipline. So I don't really recommend you doing that because an FPGA is your mathematical canvas. It is not just something you stress over and try to plug numbers in or try to do limited functions. It's a canvas. So, and DSP is a rich field, and we enhance the field of astronomy and astrophysics when we methodically and with due diligence realize our algorithms on this platform. And so we are going to look at the math. So our incoming signal exit-bin is a wideband input sampled signal, okay? Wideband means that it has a large bandwidth of frequencies. So the first thing we do here is we mix. So we mix, we're going to multiply by a complex sinusoid, and that's our digital local oscillator. And we're going to shift. And so what the mixing does is shift the band of interest down to 0 hertz. So we don't lose any information. We just take the information and we shift it all to a lower frequency. And we do that for a number of reasons, but when we're working with lower frequencies, it's easier on our hardware. And so the mixing is our incoming signal is here, our LO is here, and the frequency that we want out of exaben, out of our incoming signal, we need to tune in and mix and tune in and make our sinusoid resonate at that frequency so that we can mix it with our incoming signal to get that particular frequency. And so when we mix, the outcome of the mixing gives us a difference and a sum. And this derives straight from our trigonometric identities. So, and you can look at my previous videos, or you can review your trig, and you will see that you will get what I get. When you multiply a cosine A times a cosine B, you get the sum and difference of those arguments within the functions. So we get a difference and we get a sum. So when we get the difference, we want the difference because the difference goes down to 0 hertz. And if our magical frequency here is F1, we move everything to 0 hertz. And that's a real comfortable space for us to do further processing on. Our sum tone, we don't get what we want without getting something we don't want. I think that's like a spiritual, I think I might have stepped on a spiritual wisdom there. So we get a sum tone, but we don't want it. It's unwanted. It's far from DC. And so that is why we want this ideal low pass filter, because we want to keep the difference and reject the sum. That's what we want to do. So we design a low pass filter so that we can keep everything down here at baseband and we can reject the higher order frequencies. Now, if you remember, we have been doing this work in my class for a really long time on taking the Fourier transform of a pulse. Fourier transform of a pulse is a sinc function. And so this is our ideal frequency, our frequency response, and this is our frequency impulse response. And so this is the actual filter response that we employ, and we put these parameters of our impulse response in our FPGA, and you'll see that in a moment. But it's important to understand this relationship here, that this is in our frequency domain, and this is in our sample time domain. And these two things are connected. All right. So now we are, so again, we want to remind ourselves that we want to design our filter to keep the difference. So we want to keep this difference and we want to reject this sum product. So that's the whole idea. But because I have your attention, I'm going to talk about filter a little bit, just to make us a little bit more aware about what's going on. All right, so first of all, for discrete low linear time invariant filters, the transfer function is h of z from n equals 0 to L, and L is like the filter coefficients. We'll see that in a second. And it's h of n times z to the minus n. So this might be the first time you've even seen z's. Well, z's are the same as e to the j omega. And this is our transform in our discrete frame. So in the discrete world, we use the z transform. All right, so z is simply e to the j omega n. So this is the equation you're used to. this is a convenient shorthand. And now that you know the mapping between the two, you should be able to understand and follow what I'm about to say. So in a digital down converter, H of Z is your low pass filter. Now you can make many types of filters, but we are interested in low pass filter that keeps only the narrow band slice after mixing, okay? And that's what we want. We want our magical frequency. So now let's take a look more closely at this ideal frequency response that we have. You know, we want this area, we want nothing over here. Okay, so we have this sharp rejection region. So we have a pass band that meets this condition here, where omega is less than or equal to omega C, the absolute value, and is zero otherwise, zero phase. And we're like, yay, I want this ideal filter. And now our H of N is equal to the sinc of omega C N, pi over N. This is our impulse response of our ideal frequency. And we're like, yes, this is what I want. I want the ideal. I want the perfect thing. Okay. But let's look at some problems. Okay. You know, with perfection comes problems. So there's problems implementing this kind of thing on FPGA. There's problems building this thing, even if you didn't have an FPGA. Okay. And you're looking at real-time signals. The first thing you got to understand is we don't know what that man on the moon looks like. We have no idea what the person looks like. We have no foreknowledge. We're explorers. We're going to places nobody has ever been. And so we're trying to figure out like what comes to us. Okay. So we don't have any foreknowledge that of anything that already exists. So we need one condition that's absolutely essential is that we need a causal system. So we need a causal system. This impulse response is non-causal. Why? Because it relies on these future inputs. Future meaning, now it doesn't look like this is future, but this is in the negative. It means that we need to have known what all of this information is in order to build this filter, and we don't have any foreknowledge of this. So we can't implement this system on real-time hardware. So a causal system cannot depend on future inputs. You can't realize this. So this ideal impulse response is non-zero for n less than 0. So that's a non-negotiable. We cannot have a non-causal system. We need a causal system because we're working on real-time hardware. We're working on an FPGA. The other problem is this goes on and on forever, ever. Okay? So this is infinitely, and it's unbounded. So this ideal impulse response extends to plus and minus infinity. You can't compute infinite taps in real time, and you can't store them. We have a limited amount of space on our FPGA. So we cannot store an infinite length impulse response, because remember, this impulse response is composed of the filter coefficients that are the lines here, and I store each of these filter coefficients inside of my FPGA. And if it's an infinite amount of them, there's not enough storage, okay? Then there is something called ringing and Gibbs phenomenon. And that is an issue with this kind of brick wall. This brick wall, it is a brick wall low pass filter, okay? So you learned about Gibbs phenomenon before. And then there's no transition band. It's like, no, I want to either pass or reject you. You know, there's no middle ground with me. There's no, so anyway, I think that's another spiritual wisdom piece where, you know, this with no transition band, no negotiables, this doesn't practically work. Okay, so basically, okay, so what do we do? Let's look at the fix. All right. So you start with the ideal. You say, okay, I do want this. I know, but the most important information you get from this is what are my cutoff frequencies? All right, so what are they? And you start with the ideal, and this is great. But now the second step you do is you delay your impulse response. So you shift the whole thing over to the right. You shift it over. That's your delay. And then your sync function gets affected. Your sync function then gets a delay. And so when you introduce a delay, you're introducing a linear phase, okay? And so therefore, you're not going to have any phase distortion because all your filter coefficients, remember I said that here, are all delayed by the same amount. So that means you'll have no distortion. That's what linear phase means. And that's what you introduce here. So we're not disturbing things. And we're like, okay, that's great. The next thing you do is truncate, because remember, we can't have this thing going on forever and ever. We truncate this sync function with the window function. And these are the choices of your windows. Okay, there may be a couple of more, and each of them, there's some nuances to each of these, and they have different transition band, stop band responses. So your ideal frequency response will have some kind of transition band. It doesn't go from pass to reject. It goes from pass, and then I'll take some time, and then I'll reject you. Okay, so that's just a little bit more, relaxed. Okay, so this is a big overview of filters. I totally recommend taking a DSP course, taking a signals and systems course so that you can understand more about filters. It's a little bit more there than what I'm going over. Okay. So again, let's repeat, because we're on number 2. We don't want to get past what we're doing. Remember, the purpose of our low pass filter is that we're keeping the difference. We're rejecting the sum from that mixer. And again, I said this before, these are all of our filter coefficients. And this is the frequency response that we desire. Okay. So we start with what we desire. So, and then I repeat, that I like repeating that this H of Z, we introduce the Z transform here, where Z is just equal to E to the J omega. Now we're going to jump into, normally in a regular DSP course, you are designing filters theoretically, but I'm going to have you jump into MATLAB, but I don't want you to think that you understand this, okay? That's very clear. This is for the purpose of giving you a bird's eye view of how things are working. But I always recommend you take a deep dive to find out how the theory evolved for each of the filter methodologies that I just described. Okay, so the first thing we do, we have to define like our W sub n, which is comprised of our cutoff frequency in MATLAB. And so that cutoff frequency is scaled in this fashion. Okay, FC divided by FS over 2. So this is very important. So this corresponds to your WC, except for the 2 pi is 2 pi FC. So W equals 2 pi F sub C. So this determines your cutoff frequency, right? And N is your number of coefficients. Okay, let me stop. So I see that I've jumped on, but let's start with the first thing. The function is FIR1, okay? This is the name of the function, FIR1. And this is a type 1 filter. And again, you learn a little bit more about that and signals and systems. And also you would learn about it in my class. I've taught it in the past, and I probably will do a YouTube video on it, because what I've learned is that students really respond to YouTube video. Like in time, real-time teaching, they don't seem to pay attention, but I think back, I didn't pay attention. So your filter coefficients are these samples of your impulse response, right? Of your continuous time impulse response, which comes from your taking the inverse Fourier transform when you get this, okay? So the number of filter coefficients that you choose is called N. That's your number of filter coefficients, right? And the more you have, sometimes the better, sometimes, but you kind of just want to meet your requirements, because more is not always better, because when you think about filter coefficients, you're impacting the block RAM of your FPGA. This is your cutoff frequency, and it's determined by this equation. You want a low pass filter, all right? And then I'm choosing this window, okay? And you can look at the frequency responses of these various windows. I probably will have a MATLAB a homework problem on this. And then this parameter scale. So what you get at the end are all your filter coefficients. This is a number of filter coefficients that you want. And then the result is you get your filter coefficients. That's B. Okay. So now that you've done that, we got to remember that we are still working with the same equation we've been working with the entire time. And that is that what we're doing is we are multiplying our mixed signal by our low pass filter. That's what we're doing, right? So what do we need to do here? In MATLAB, y of n equals filter of B, and you put a 1 here because it's a FIR filter, and then what you are filtering, and that's our X mix. So that's how you get your y of n. All right. So now we have finished filtering. All right. That doesn't mean you understand filtering. That means we have finished filtering. I've shown you how to do it in MATLAB, and I've given you the reasons why. And so number 3 is downsample by M. Okay. So we want to reduce the sample rate because we have our magical frequency now at 0 hertz. So now we can reduce the sample rate. So you stretch the original spectrum by M. And what does that mean? Because you keep 1 out of every M samples. I see students getting mixed up with this all the time. I found this example and I felt like this was good. Say you have X of n is equal to cosine omega naught n. And you were to scale this by M. So that means that every M sample you're taking. So when n equals 1 and M equals 2, then you're taking the second sample. When n equals 2, M equals 2, you're taking the fourth sample. M stays 2, but n is going to 3. You're taking the sixth sample. So you're taking every other sample. That means you're downsampling. What does this look like in frequency domain? Well, right here, you got cosine omega naught, and you're doing M times N. So what is your frequency? Your frequency is multiplied by M. So that means your frequency is scaled by M. So guess what? That's why your frequency is larger. So it's M times omega naught. Okay. So if your frequency is 2 hertz and M is 2, you're going to have 4 hertz. And so that's the effect of downsampling. When you reduce the sample rate, you increase your frequency. Okay. And then these are the equations that support the theory, okay? And so your low pass filter, with that in mind, must be tight enough that after you downsample, the aliases land in the stop band. Remember, if your frequency grows, then that means like when you downsample, if you come out of your downsampling with a bigger frequency than your reduced sampling rate can support, you are going to alias. You are going to have a problem. Okay. So there is another great video that I have created. And I think that that one involves looking at a chirp signal. I would definitely, and it's for cloud radar, which is another research, uh, 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 another research project in my group. So I would recommend that you look at that. So downsample has implications because of the fact that your frequency grows. Okay, but I just want to point that out. Now, so now I think we have a better idea of what is going on with our with each component of our single down converter, digital down converter. Now we understand what the mixing is doing. We understand what the low pass filter is doing, and now we know what the downsampling is doing in terms of equations. So now let's start to look at, let's put two of these. Say, for instance, we want two magical frequencies here. What are the implications on my FPGA? As you can see, the resources double. That tells me a lot. Now, remember, I want to see these particular frequencies, and I want to see them well. I don't want anything around them. And that's why I want a good low pass filter. So this is the reason I'm using this single down converter, digital down converter. Okay. But now let's look at the we want to see more frequencies because NASA never sends an instrument up in space that only looks at maybe a few frequencies. And usually we want the most bang out of our buck. So we are sending an instrument that can look at a forest of frequencies. So we want the whole bandwidth. We want to go from 0 to 500 megahertz. We want to see everything. Okay, so if we want to see everything, and we want to see it in a great way, like, filtered properly, well, then we have to have unique LOs for each one, unique filters for each one because they're at different frequencies. And so, wow, let's see, what kind of resources is this going to take? Remember, you're supposed to look up how many of these resources are in a Xilinx RS SoC FPGA. So assuming all of these design parameters, we're looking at lookup table usage at 425K, DSP slices at 4272. Wow. Block RAMs at 1080. And this is everything that I looked up said that it's over this amount. So you're looking at using more resources than even what you have. And at the end of the day, you're only getting frequency content out of this. Well, frequency content is the first stage of any of our FPGA work. After we get to frequency content, that's when you want to do your eloquent math. But according to this table, you can't do anything more than just looking at the frequency, and you really can't do that. So, like averaging, you're not going to be able to do that. You don't have it. You've run out of resources. So then, I must say in completeness that this is not the FPGA that we fly. This is not for space flight. This Xilinx RS SoC FPGA is not space qualified. We use a different FPGA for space. Okay, and that's the Xilinx ultra scale, Xilinx Kintex ultra scale FPGA. All right. Now, what did ChatGPT say to this? Since that's what your students are really into, right? It says, don't build 500 separate DVCs. That would explode resources. Use a Polyphase FFT channelizer, and you will fit comfortably on an RF sock. Okay, so ChatGPT informed me. So now, how do I evolve and create something I never heard of, a Polyphase filter bank, from this DDC? Okay. Let's first look at this DDC a little bit more, even another layer. Now, the first thing I want to say is I'm going to share some disparaging news about this DDC, but it really isn't. This is something that's widely used, but it's used with skill. Somebody that really kind of understands DSP, that understands radar, that understands what they're doing in a frequency plan. But I'm really kind of trying to explore to you how we're going to take the challenging aspects of the DDC and turn them into evolving us into the Polyphase filter bank. All right. Now we got to look at what we're doing. Our incoming science signal here is sampled at FS. So that's clear. Our ADC is sampled at FS. So our whole system is running here. This is the rate that all of our data is coming into an FPGA. The first thing that we do is we mix, okay? Because we want to translate this tone to a lower frequency. All the information in here never gets lost. We just transfer it to a different frequency. A lower frequency. It's sort of like if you're driving a car and you have your child in your car, and your mom is coming, and you're going to take the child, and the child's going to go with grandma, and they're going into the car. So you pick up the child, and the child goes into the other car. The child hasn't changed. The child is still the same. It's just that we've transferred the child to a different car. That's how you need to think about mixing. Mixing does not change anything. It just translates it. It moves it. And we need it to be moved because we always like to work with lower rates. Okay. So FPGA resources here, it costs us LUTs, block RAMs, DSP blocks. Okay. So now we need to design a low pass filter to reject the sum product. And we already know what that is. Again, we're using our filter, we have to store our filter coefficients. That requires memory and DSP resources. All right, next, great, we're downsampling because we got all of our signal. That means like the child is in grandma's car. And that means the mother can go home and go to sleep. Great. And that means that now we can relax our sampling frequency. That's why we choose downsampling. And so the frequency is at baseband. We can lower our sampling frequency, and our new sampling frequency is now FS over M. Great. So we've thrown away samples, but we've thrown away samples after we use all of these FPGA resources. So what does that mean? You use all of these resources on the FPGA only to throw out all of the samples. Now, does that mean we don't use a DDC? Absolutely not. I use it all the time. I'm using it in a current radar project. So under specific conditions and with understanding, I use this. But this is the basis for deriving the Polyphase filter bank. And so now let's go into thinking about that. So we know that we're throwing away samples here. We know we have a low pass filter. We know we have this, and we know we need to see our magical frequency. But now we need to see more. We need to see all of our frequencies all at the same time. And we don't want to use like 500 of these things. We can't. So what do? We go to our graduate level course called Multi-Rate Signal Processing, and we read our book by Fred Harris. I must have read this book over and over and over again. I'm still reading this book over and over again. I mean, he's brilliant. I got the privilege of taking a week-long course with him, and I've never seen anybody so enthusiastic with signal processing. That this was absolutely not my favorite course in undergraduate. Okay, so now we are looking at finding DSP techniques where we can leverage our skills and go into a different, take the DDC into the polyphase filter bank. And what we find is we can apply the noble identity, and we can switch the order of the down sampler and the low pass filter. And this is called the noble identity. This is found here. So I would look at the book and learn about this a little bit more. And I'm going to tell you why. This is only for under certain conditions. What this would require is that the filter architecture will change. See, the polyphase filter bank heavily relies on understanding the filter. And we're going to go into that. Okay. And then because this is hanging out right here, it doesn't matter if we multiply or mix here or mix down here. And so that's what we do. We slide the mixer through. So the first thing we do is we apply the noble identity and switch the low pass filter with the down sampler. And then we determine that we can slide this mixer to the end of the line. And so right here, we have a different kind of signal flow than up here. I'm making this simple so that you can read through here so that you can fully understand it for yourself, okay? And now it's important to understand what is the architecture of a traditional filter. This is it. It's made of chained delays, right? Chain delays multiplied by the filter coefficients, right? So if I have 16 filter coefficients that I want to multiply my incoming signal with, and this is the impulse response of my filter, right? Then I would build such a structure. And in my class, the third homework assignment, this is what I have students build so that they are already in touch with, they're already doing filtering before they even know that they are. Okay, so my H1, this is my filter coefficients are here, and my HN is here. And this whole side replicates. Okay, so there's unique things that you can do so that you can save resources and not use taps for things on this side that are repeating. All right. So I just implemented this equation, the convolution equation. This is your filter structure in your FPGA. This is what you build. This is the traditional. Okay. Now we're going to look at how do we look at the traditional and change our traditional implementation to our polyphase implementation. And so first of all, we have a length L filter coefficients from our impulse response, H of N. Decimation is M, that's our downsampling parameter. And what we're doing is H of N is split into M downsample subfilters called polyphase components. And this is the mathematical equation that shows you how that structure presents itself in the architecture. So each color is a different phase of H of N. So, and that's what you can see here. So you keep up with the colors. And each color is a row. So each color is a row in your new structure. So where this structure would be all one row, I still have all my filter coefficients. Everything I would normally have, I just arranged them in this particular way. I've downsampled them, and I'm operating, and I make a sub-filter for each row. And that preserves me from aliasing, because I have incorporated downsampling into my low pass filter. I have combined filtering and downsampling into one thing, okay? And so what is the equation for this? This is my subfilter, e to the m of z, and then it equals this equation. And so this equation will map to each of these rows. So you use this equation to inform you of each row. And so each row comes from z to the minus L. And the coefficients for each row is composed of here. And as an exercise, test this. Test this with real numbers. Make M4 and make L, like L is your total number of coefficients. Okay. And so this is a finite impulse response with linked L coefficients and L sums from L equals 0 to L over M minus 1. Right. So for those who have built the baby PFBs, test this formula for your baby PFBs. Those who have done it know what I'm talking about. Okay. Always put in real numbers when you are developing your equations. All right. So now let's look. We got this guy out here. We have downsampled our filter, and we took care of both of these things. So this is why it's so important that with DSP to learn it and relearn it, because the richness of DSP makes for the more sophistication of your algorithms on your FPGA. When you understand these nuances that are there, and that have been there. So the noble identity has actually changed the way we are designing our filter. And we're not violating Nyquist, we're not violating, we're not aliasing, and we have combined operations here. All right. So what have I done? What am I about to do? Like right here, this e to the j2 pi f1 over fs, okay? This serves the one. It serves the one frequency. But I can use an endpoint FFT, and I can take care of all frequencies. I can take care of them all, because I want the whole bandwidth of data, right? I want every frequency. So as K gets incremented, I'm getting everything out of my design. All right. So this serves the many, and this serves the one. So yeah, this still serves the one. So now, how does it serve the many? Yeah, voila. That means that at the end, in order for you to get all your frequencies simultaneously, you will have latency, by the way. At the end of your polyphase filter structure here, you put an endpoint FFT, and this takes care of your complex multiplications, your E to the J 2 pi Km. This is like your LO. This is your LO. Okay. And this is your downsampling plus your low pass filter. This is your DDC for the Polyphase filter bank. And this is what Fred Harris explains so well in his book. Okay. I can't do that enough justice. But in order for anybody who is understanding Polyphase filter bank, I believe, I shouldn't say it's a rule, I believe one needs to start with the DDC. It was the way I learned it, and it resonated with me, okay? Now, more equations, yay. All right, so now we got our filter, and we have downsampled our filter. That's why we have this M here. We have downsampled our filter. We have our subfilters here. And we have described what EM of the Z is in terms of our single low pass prototype filter impulse response. Remember, we only need one filter. That's what's powerful. To service all of our frequencies, we need one filter. And then our filter coefficients are mapped in this array. And these are the tops. Okay? So each row is a downsample version of our prototype filter. And here, this is the phase demultiplex and subfiltering. So essentially, we are multiplying our we're downsampling our input signal because each leg of our polyphase filter is delayed, right? So X0 goes here, X1 goes here, XM goes here, and then we circle back, XM plus 1 goes here. It's like you're playing cards, all right? You are dealing out at the same rate, but everyone around the table is getting their cards at a different rate. And that's how your input signal is getting fed into your structure. You are still sampling at the same ADC sampling rate, but with a series of delays, you are delivering your samples to your subfilters at a fraction of that rate. Therefore, you're able to keep up with your entire data rate. You may need to pause and repeat what I just said, and also read Fred Harris. All right. So your incoming signal is downsampled as well. And it's multiplied by E of M. And then at the very end, your DFT, your channel subband outputs, are fed into an endpoint DFT. And voila, you get your magical frequencies, all of them, not just one, but all of them. All right. And so here, M is your downsample parameter, N is your length of DFT. As always, please, place a message in the chat, is it in the chat? Yes, in the chat, something like that. I'm talking online all the time, so many times I don't even know when I'm on Zoom or off Zoom. So anyway, you place your comments into the chat, subscribe, and we will move on, because this is just understanding the theory of the polyphase filter bank and the derivation and the roots of where it comes from. The second and most essential part of this is building our MATLAB frequency plan, followed by our Simulink frequency plan, deploying things on an FPGA and testing it on real-time hardware. That is all a part of this. So this is your first kind of encounter with the Polyphase filter bank. I encourage you to subscribe so you can look at my subsequent videos. Hit like, hit subscribe, and see you later. Have a great rest of your day. Bye for now.